I was asking about this equation of the scale factor. Um, Now, I don't really think that the scale factor exactly has a lot of merit, but it's hard to explain why succinctly. So let's go into the Susskind lecture and see if I can follow along, and I'll make objections as I see them. Okay, the link brings us to a part of the video where Leonard Susskind is pointing to this particular equation on his whiteboard, and I think once you decide this is the equation that you're using, then of course it does have a solution. But we'd like to go back earlier in the video and see where this particular equation came from. And the equation came from an escape velocity equation. It basically came from this uh, conservation of energy requirement, 1/2 mass times the escape velocity squared equals gm over r. Do I need the negative sign there? I don't think I need the negative sign there. Now, how do I get from this to this? Okay, he has the equation written on the board at 5912. Actually, he hasn't quite finished writing it.
Squared, just r.
And actually, I don't quite have it written quite right. I got to correct that and then cancel out those m's. Now, this is actually setting this thing equal to 0. If we set this equal to 0, we get that. Now, this is a special case, though. It represents a situation where the particle m moves away from particle m towards r approaches infinity at a velocity asymptotically approaching 0. In that example, the universe is at a critical point. If this was just a little bit greater than 0, then the velocity would not asymptotically approach 0. If it was just a little less than 0, the velocity would come to 0 and everything would fall back into the would fall back towards the center. However, if 1/2 mv squared minus mmg over r is less than 0, that's basically energy per particle. This is kinetic energy, and this is gravitational potential energy. If the kinetic energy plus gravitational potential energy per particle is less than 0, then what would happen is that the particles should collapse back to the center. The particles should collapse back to the center if that center existed, which unfortunately in this case, though, that center does not exist. In the description that Leonard Susskind has been describing up to this point, he's been describing an infinite homogeneous distribution. So there is no center, and there is no force on any particle in this situation. But still, I think it'll be fun to just kind of run through the math that Leonard Susskind does to show how we get from this equation to this equation. And by the way, if we had a distribution of matter that was homogeneous and it extended out to a finite distance r, then this would be a perfectly valid reasoning. The trouble is that he's using this in a distribution where the distribution is supposedly going out for infinity in all directions, in which case there is no escape from that distribution, so there is no escape velocity. You're just embedded in that infinite distribution, and there is no force on you, regardless of where you are within it. So I am going to change the parameters of the question. I am going to just ignore the silliness about infinity so that this equation actually does apply. We're going to say that we have a finite spherical distribution of matter that is homogeneous up to the edge, but beyond the edge there is nothing. And I will call this the finite Friedmann distribution. Um, this is not to be confused with Milne's distribution in any way. This is finite Friedmann distribution. And with that finite Friedmann distribution, we can assign a scale factor to it. We can say that for any individual particle in that distribution, the distance to that particle is going to be a of t times its velocity. It's actually going to be t times its velocity. It's going to be its velocity times time. Now, I've done this before on my spoon-fed relativity articles. Where was it? It was under, it was under the uninformative title Hypothesis versus Impression, I believe. Was it under Modeling SN1A Data Minkowski style? Here it is. Assuming a diffuse uniform sphere of constant density, this leads to 1/2 mv squared equals gmm over r. Let's follow this. And notice that what I'm assuming here is explicitly not what Susskind is assuming. I'm assuming a diffuse uniform sphere of constant density rho, but this sphere does not extend out to infinity. It extends out to a finite distance. So with our first thing here, I'm replacing m with the density times the volume. And I think this must be a typo because I don't think I use that later. Okay, with the second thing here, gm rho v, gm rho, there's our volume. I'm replacing volume with 4 pi r cubed over 3. And notice this is where I'm invoking the shell theorem, because this volume here is the volume of the internal sphere. It only extends out to r, which is the position of the particle, not the r of the whole sphere. And then this isn't an equality, it's an implies. So at this point we have 1/2 mv squared equals gm rho 4 pi r cubed over 3 divided by r. We cancel out the masses, and we will multiply the 2 over there, so it's 8 pi r cubed over r. R cubed over r is r squared. G needs to be in there, rho needs to be in there, equals v squared. Divide both sides by r, we'll have v squared over r squared equals 8 pi r. R squared, no, I don't need that. G rho. And then I left out the 3, so let's put that 3 in there. And now we have v squared over r squared equals 8 pi g rho over 3. And what will we do then? We'll replace, well, at this point we could say a dot over a squared, because this is the velocity is basically the change in the r position over time, equals 8 pi g rho over 3. The trouble is that the density is also changing over time. And I think this is probably where I could do something with this web page, because actually I need to take into account that that rho is a function of r somehow, and I didn't get to that point in this video. Because if we've got the positions of the particles is x equals vt, v, then there's going to be something to do with the equipartition of the velocities. The equipartition in v relates to the density function in t. How can we make that into a mathematical? I mean, I can see already I could just simply replace this with a proportional symbol. A dot over a is proportional to 8 pi g over 3. We don't even need that constant now. But the density is proportional to, it's going to be rho of t, and the rho of t is going to be proportional to 1 over a cubed. But if we wanted to keep that constant in there, we need to like specify exactly how these different velocities are set up. Now, why does this fall apart if we assume an infinite distribution? Well, if we have an infinite distribution, there's just no reason to select some center for the shells other than the object itself. Every object is surrounded by an infinite amount of matter, therefore every object is not accelerating. Now, you might call me stubborn, and am I just being stubborn and saying, no, I do not accept that? Yeah, perhaps I am. I'm just putting my foot down and saying there's no reason to say m is accelerating in an infinite distribution of homogeneous distribution. Now, I say there's no reason. However, I mean, I do confess I have heard the reason. The reason that people give is that, well, we're at the origin, that mass is over there. Therefore, of course, we're going to draw a series of concentric shells around this point. And we're going to count, okay, this amount causes that mass to accelerate this way. This shell causes that mass to accelerate this way. This shell causes that mass to accelerate this way. This shell causes that mass to accelerate that way. And this shell makes this mass accelerate that way. And then this shell, well, that mass is inside that shell. So that shell does not contribute anything to the acceleration of m. And this shell does not contribute anything to the acceleration of m. And they just keep repeating and repeating and repeating this argument ad nauseam, and saying, oh yeah, we do have this reason. I say what you're doing is you're using something called the Riemannian Rearrangement Theorem. What you have is an infinite number of discrete masses in the space, and you're making a choice, and what happens is that the sum of all of those infinite contributions of force is going in various directions, and in the end you can make that sum equal anything you want it to by changing the order of what you are adding, and it's called Riemann Rearrangement Theorem. Now, what I am saying is there is no reason to add up these discrete masses in this order, starting with somebody a billion light years away from the mass and adding up consecutive shells to get a force going this way. I say that there is no reason to do that. Um, and but then what people continually repeat is, I just did. Now, the question is, does I just did add up the things in order to get that sum? I just did. Is that a reason? Does that constitute a reason for doing it? I can do it. Yes, you can. Okay, yes, you can add things up in that order and get that result. Yes, you can. The question is, why? Why did you do it? And it does not matter how many times you repeat, I just did it. The question is, why did you do it? And I don't think you have a good answer for why you did it. Or I've offered some, like one answer I offered, I said, you could say the observer is supreme. And in that case, you say, okay, well, I did it because I believe that this observer's perspective on reality is super relevant to him in that following manner. And I use this argument in a different context when I'm talking about special relativity, and in particular um, the application of the Lorentz transformations. I do say the observer is supreme. I want the coordinates of the events to be figured out. If you're asking what that observer sees, then you need to convert the coordinate system to the situation where where the observer's velocity is zero. And once you do a Lorentz transformation to convert the observer's velocity to zero, then the coordinates of the events that the observer is seeing is the correct positions of those events for that observer. And so I would use this this particular argument to defend the use of the Lorentz transformations to find a to find the coordinates of events. But I would not use uh, the observer as supreme as an excuse for doing this, because regardless of my perceptions on reality, my perceptions on reality are not going to create a force on this distant particle. They might affect the coordinates where I see that a force being applied on that particle, but they won't affect the event of this particle accelerating or not. And so that is why I say you have no. So 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 this is a reason. I could at least acknowledge this is a reason. I don't think that a reason would be correct in this situation, but we're not getting to that point in the argument, because instead of answering why did you do it, I keep saying why did you do it, and the answer is I just did. And I don't think that's a good answer to the question why did you do it. The fact that you did it is not an answer to why you did it. Okay, thanks for watching.